But first, we are going to start with Dr. Soumya Das, who is joining us from Netherlands. And to tell you about Dr. Soumya Das, he's a quantum communication expert, currently serves as a postdoctoral researcher at Eindhoven University of Technology, contributing to the Quantum Delta NL project funded by Netherlands government. He is PhD in quantum computation, information and cryptography from the Indian Statistical Institute, Kolkata. Dr. Soumya Das focuses on quantum communication and security in his current research. So we have with us Dr. Soumya Das ji. Dr. Soumya Das, we welcome you in this session.
Hello. Hello.
Yeah, Dr. Das.
Can you see the screen?
Welcome to the session. Can you hear us?
Yes. Can you see the screen?
Yeah, please, please.
Okay. So, thank you for your kind introduction. So, this is Soumya. So, I am working as a postdoc and Netherlands Quantum Delta NL project. So, first of all, I would like to thank the organizer for inviting me here, and I'm honored to present my talk on navigating the landscape of continuous variable quantum key distribution, recent progress and open challenges. So I will start with a brief introduction of quantum cryptography, the core aspect of CV-QKD system. Then we'll explore the CV-QKD theoretical challenges and implementation details of the CV-QKD system. And then we will share some insights of the CV-QKD work at Eindhoven University of Technology. And finally, I will share quantum communication work in Netherlands and what India is doing in CV-QKD with some references. So a brief introduction to cryptography. We know that communication, if that is public between Alice and Bob, then no cryptography is needed. If the communication is secret, then attacker can hack this information, so we need cryptography. Now, if the communication between Alice and Bob can be done in two ways, so if they can encrypt and decrypt their information using same key, that is known as symmetric cryptography, and if they use different key, that is known as public key or asymmetric cryptography. Now, Peter Short in 1994 has shown that using a quantum computer, this public key crypto system
Dr. Das, I'm
can be
extremely
broken.
sorry. My apologies. Actually, I'm interjecting in between, but your screen is not visible, so I've been asked to actually share your PPT, please, once again. Thank you.
Okay.
Okay. Yeah.
You can see the screen now?
Yeah, it's quite visible, but then it's not changing actually. The slides, the PPT is not changing.
Is it changing now?
I'm afraid it's still the same. If you can just communicate and help with it.
Sir, please start sharing your screen. Start sharing your screen, please.
Okay.
It is uploaded, sir. He is not sharing his screen actually. It is preloaded screen actually. Yeah, sir, please don't stop share. Don't press
Okay.
stop share. Yeah, that's better, sir.
Okay.
Please. Now, whatever you will do, it will be visible to us. Yeah, it's fine, sir. Thank you.
Now it's clear.
It's clear, sir. Thank you.
Okay, thank you. Sorry for the disturbance from my side. So let's start once again. So this is Soumya. So I'm working as a postdoc in Eindhoven University of Technology. So I welcome you all to this session of navigating the landscape of quantum key distribution system, recent progress and open challenges. So I will briefly introduce what is quantum key distribution, what is the CV-QKD system, the theoretical challenges, implementation details, what we are doing in CV-QKD at TUE, and the quantum communication system in Netherlands, and finally some references. Okay. So a brief introduction to cryptography. So as we know that Alice and Bob, they can communicate the public information, then no cryptography is needed. If they share some secret information, then we need cryptography. Okay. Now, as we know that this can be done in two ways. If Alice and Bob uses the same key, then that is known as a symmetric key cryptography, that is previously shared key. If they use different key, then it is asymmetric key cryptography. Now, Peter Shor, as we know in 1994, has shown that using a quantum computer, they can break the public key crypto system. So we can use either post-quantum cryptography to secure our system or quantum key distribution. Now, quantum key distribution can be done in again two ways. One is discrete variable approach, one is the continuous variable approach. Okay. Now, why CV-QKD? So we have DV-QKD and PQC. In PQC, we have computational security. In DV-QKD, we have information theoretic security. For PQC, we have high speed, whereas DV-QKD is low speed. PQC low cost, DV-QKD high cost. PQC is compatible with our current classical system, whereas DV-QKD is very incompatible as it requires single photon detector and a single photon source, which is inherently very costly. And finally, the distance allowance. So DV-QKD is short distance, whereas PQC is long. Now, where stands this CV-QKD? CV-QKD takes all the advantages from DV-QKD and PQC in terms of it is information theoretic secure, high speed, low cost, compatible with current infrastructure. But one of the issue in obviously CV-QKD, it is short distance, but recently our group has a result that CV-QKD can go for arbitrary distance that I will share later. Now, what is DV-QKD? As we know that in DV-QKD, the qubits can be realized in photon polarization, electron spin, or electronic states of atom, which is based on the no cloning theorem. Where in CV-QKD, it is based on the Heisenberg-Isensky density. So in CV-QKD, we encrypt information in the phase and amplitude of a coherent pulse, where the short noise is the inherent noise of this coherent pulse and the excess noise is what we measure at the receiver end. So this is CV-QKD is in terms of communication using noise. Now, what are the components of a CV-QKD system? So, major components is obviously laser, which can be pulse or continuous wave. Then we apply some modulation. So, modulation can be either Gaussian or discrete. Then we can have transmitter monitoring, which is source or injected light. Now, this information is sent from Alice to Bob using optical fiber or free space communication. Then at Bob end, it have a receiver monitoring, which can be again local oscillator or injected light. Then Bob can apply demodulation, which can be either synchronization or optical compensation. Then it can have a detection, which is homodyne or heterodyne. Now Alice and Bob can have the classical post-processing using authenticated classical channel. So previous one was quantum channel. This is classical channel. So Bob can apply shifting if they have used the homodyne measurement. Okay. For heterodyne, this step is not needed. Then they apply a parameter estimation, which is just discarding some data and estimating the parameter of the channel. Then they apply error correction, which is either LDBC, turbo, or some other code. And finally, the privacy amplification, that is hashing. And after that, Alice and Bob have the raw key. Now, in this scenario, as what will be a simple attack model? Okay, so Alice and Bob is communicating, and attacker can generate an EPR pair, entangled pair, and he can mix with Alice's signal, and again using a beam splitter, he can take some portion of the signal and some portion of the EPR pair goes to Bob, so that finally the data that attacker has, that is correlated with some Bob's data, and Bob's data is also correlated with attacker. So in this way, attacker can gain some information without being detected at Bob end. Now, in theoretical development of CV-QKD starts from 1999, where the first proposal using quadrature has been proposed. In 2005, in between 2001 and 5, we have CV-QKD using Gaussian state, that is the famous GG02 protocol, and we also have reverse reconciliation and no switching protocol. In 2005 and 9, we have asymptotic collective attack, multi-dimensional reconciliation, and finite size analysis. In between 2013 and 15, scientists have developed MDI protocol, finite size effect, and first composable security proof. In recent year, in between 17 to 21, the Gaussian definitely reduction, asymptotic collective for 256 QOM, and short noise calibration, and finally in 2023, point-to-point and multi-point protocol has developed. Now comes the real issue, what are the theoretical challenges? Okay, most theoretical challenge in CV-QKD domain is the security analysis. Why? Because security analysis is dependent on several parameters. First, what is the state you are using? It is coherent state, squeeze state, or thermal state. Second, what are the modulation techniques we are using? Is it continuous variable or a discrete variable? Third, the measurement we are using. Is it a homodyne measurement or heterodyne measurement? And the type of protocol we are using. It is a one-way, two-way, or measurement device independent. And we have some tools for security analysis, that is the uncertainty principle, linear semi-definite programming, non-linear semi-definite programming, or entangled photon pair. Now, if we use Gaussian modulation, the implementation is very challenging, but the security proof is feasible. We have composable security proof. But if we use discrete modulation, such as BPSK, QPSK, 64 QOM, 256 QOM, and we can increase the number of QOM, that is quadrature amplitude modulation. Now, as we increase from BPSK to 256, the implementation becomes more challenging. But the security proof, the implementation is challenging, but the security proof is feasible, right? For BPSK, say the implementation is feasible, but the security proof is very challenging. But as we increase the number of QM, the implementation becomes very challenging, but the security proof is feasible. Next challenge is designing a very good error correction code. Traditionally, what most of the people is uses LDVC code. There is other option as turbo code, polar code, raptor code, and finally, that is our team developed a simple random code book, which shows that if we use this type of code, the limitation of the distance that I tell above is lifted, right? I will tell you later for this one. And using this code, what we will do, we will calculate different properties such as SNR, signal to noise ratio, frame error rate, reconciliation efficiency, and secret key rate. Now, what are the state of the art? We know that in lab system, so it is achieved like up to 202 kilometer, and the key rate is 6 pps, that is in China, and 100 kilometer is also from China, and France is also doing some lab test. In a field demonstration, 50 kilometer again done by China and 17 kilometer by France, and for chip-based system, 50 kilometer again by China, right? Now, what all this implementation, what is again the real challenge of implementation to make a real-time system, such as the post-processing of the system should be in real time. That will be very useful for real-life scenario, for practical implementation. Interestingly, none of this implementation has made a real-time situation. So real-time system means all the post-processing in Alice side and Bob side, that will be in the real time. So this is the main challenge that we need to understand. So in theory, we have security challenges. In implementation, we have the distance challenge and the real-time implementation. Okay. Now, what we are doing at Eindhoven University of Technology, we are really focusing on real-time systems. So till now, we have achieved a real-time BOP in free space communication with 2.7 Mbps, that is equivalent to 20 kilometer fiber, and we have used 256 QM. And interestingly, the component we have used, that is the real life and low cost component. We have characterized the turbulence in the free space channel, and as real life scenario requests co-propagation with classical signal and quantum signal, we have also demonstrated. Now, in the error correction code, we are working on three types of code. One is LDPC code, where we have achieved optimized low rate for LDPC code, and we are working very close to capacity. And we have researched the practical consideration for reconciliation of CV-QKD. And secondly, we have started working on turbo codes, where the results are submitted. And finally, this is random codebook. This is a very new paper came out in the last week, where we have theoretically designed using Gaussian modulation an error correction scheme that gives positive key rate for arbitrary distances, right? So that means if our research is good and it's true, then we can get the secret key rate, that is a positive secret key rate for arbitrary distances. Then our limitation for the distance will be lifted. Okay. And in future, what we are really focusing a real-time Alice and real-time Bob. That means we are focusing on a real-time system. And till now we have done experiment in free space. We can do in fiber also. And finally, the most important one, we now perform the experiment for this random codebook error for discrete modulation, that is practically used and taking all the practical consideration. This will really be change the way that we look in quantum key distribution system, right? So this is in summary our work at Eindhoven. What are the commercial CV-QKD systems available? So Quantisense Lab, they have made a CV-QKD system that is a coherent state Gaussian modulation and using homodyne detection. They have also told in their brochure that they have used finite key effect and their raw key rate is given, but maximum distance is 40 kilometers. Another company, Lux Quanta, they are also working on CV-QKD system, and KeyQuant, they have told they are also working on CV-QKD system. Now, what are the other projects of quantum communication in Netherlands? As I told that I am a part of National Quantum Mission of Netherlands, where we are working on three categories: quantum computation and simulation, building quantum communication network, and quantum sensing application. I am a part of building this national quantum network in CAT2 project. So we are aiming for a test bed both in DV-QKD and CV-QKD. And the funding that Quantum Delta NL has, 62 million, that is from Dutch government, and QSign, this is from EuroQCI, the people from the previous talk, they have told it has 10 million. And what is our planning? So this is the map of Netherlands. So this is TUE. We are now have achieved that DV-QKD between TUE and Walre, 7.7 kilometer. And we are planning to have this connection at TUE between automotive high-tech campus and Walre. And at Utrecht and also in Amsterdam, they are also building this network. So final goal is to build this quantum communication network in Netherlands and also quantum communication network with other EU countries. Now, as per we know that RP Singh group has in PRL has recently started this free space quantum key distribution with discrete phrases that come last year. I think RP Singh is a speaker here and he will talk more about their work. CDOT has recently started its development of CV-QKD and they have released a proposal last year. And TCS is also monitoring the progress of CV-QKD towards the software side, building some software infrastructure. This is our team at TUE, and we also have a startup that is working on a real-time chip-based system and making a product from our research. And I will end my talk with some very good survey paper, which if you wanted to start your research, you can really start among these survey papers, where I would recommend this paper came out in 2023, CV-QKD, and if you just start looking on this paper and you will get sufficient information. And this is our papers at TUE, and I really wanted to focus this paper, CV-QKD with key rate. This is recently came where we have told that really CV-QKD can lift the distance barrier. Okay. And I will, this is my last slide. So if you want to connect with me in LinkedIn, you can just scan this picture and you will be immediately connect. And as you can see that I have masters from Indian Institute of India Shibpur, IIEST, and PhD from ISI Kolkata under Professor Gautam Pal, who is also a speaker here. And then I was 1 year at TCS. And finally, I am here at TUE. So thank you for listening. And if you have any question, then I am open for taking questions.
Thank you, Dr. Soumya Das, for joining in from Netherlands and sparing time for us and speaking on advancements in quantum key distribution. Ma'am, can we take some questions in between or shall we continue later? Okay, sure. So, ladies and gentlemen, that was Dr. Soumya Das from Netherlands. And now we have Dr. Anirban Pathak with us. Professor Anirban Pathak is a theoretical physicist. He did his PhD from Vishwa Bharati, Shantiniketan, India. He was a postdoctoral fellow in Free University, Berlin. Dr. Anirban Pathak is a professor and head of the Department of Physics at JP Institute of Information Technology, Noida. He is actively involved in teaching and research related to